You think you know what comets look like? Ice balls from the edge of our solar system, predictable tails of dust and gas streaming behind them as they race toward the sun. But on July 1st, 2025, something different showed up in our telescopes. Something that breaks every rule we have about how space rocks behave. Something that Harvard astrophysicist Avi Loeb calls a 6 out of 10 on his alien technology scale. 3. Iatlas arrived from the direction of Sagittarius, moving at 58 kilometers per second, fast enough to escape our sun's gravity completely. That hyperbolic trajectory tells us one thing for certain. This object came from another star system. But everything else about 3 Iatlas defies explanation. It started glowing when it was still 6.4 astronomical units from the sun, way beyond Jupiter's orbit. Most comets wait until they're inside 5 astronomical units before they wake up. 3. Iatlas didn't wait. If you value documented astronomical research like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. The script is researched and factual. Using sources from NASA's James Webb Space Telescope observations, published in August 2025, and SphereX mission data from the California Institute of Technology, published on August 21st, 2025. Now back to the information. The numbers don't lie. When NASA's Transiting Exoplanet Survey satellite went back through its archives, they found 3 Iatlas glowing bright as early as May 7th, 2025, 2 full months before official discovery. The comet was already active at 6.4 astronomical units from the sun. That's unprecedented. Water ice doesn't sublimate at those distances. Something else was powering this brightness. Enter the James Webb Space Telescope on August 6th, 2025. Its near-infrared spectrograph cut through the mystery like a scalpel. The data showed something that made astronomers around the world stop and stare. 3. Iatlas wasn't just unusual. It was impossible by our current understanding of comets. The carbon dioxide to water ratio measured 8 to 1. 8 to 1. That's the highest carbon dioxide concentration ever recorded in any comet, anywhere. Think about what that means. Solar system comets typically show water as their primary volatile. 3 Iatlas flips that completely. It's pumping out 129 kilograms of carbon dioxide every second versus just 6.6 kilograms of water. This isn't a normal comet composition. This is something that formed in an environment we've never seen before. The SphereX Observatory confirmed these findings between August 7th and 15th, 2025. Multispectral observations revealed a carbon dioxide coma stretching 348,000 kilometers in radius. For perspective, that's nearly the distance from Earth to the Moon. All carbon dioxide gas glowing bright in infrared wavelengths invisible to human eyes. The nucleus itself measures between 0.4 and 5.6 kilometers across, but it's producing a gas envelope the size of a small planetary system. Harvard's Avi Loeb published a controversial paper on July 21st, 2025, asking a simple question. Is the interstellar object 3 Iatlas alien technology? The paper hasn't been peer-reviewed, but the arguments are mathematically sound. 3. Iatlas approaches Venus, Mars, and Jupiter with a probability of less than 0.005%. That's not random, that's targeting. The trajectory itself tells a story. 3. Iatlas reaches perihelion on October 29th, 2025, on the opposite side of the Sun from Earth. Perfect timing to avoid detailed observation during its closest approach. The retrograde orbit lies within 5 degrees of Earth's orbital plane, a coincidence with only a 0.2% probability. When Earth and 3 Centaurus Atlas meet in December, their relative velocity will be 98 kilometers per second. Too fast for any human-made spacecraft to intercept with chemical rockets. But here's where it gets truly strange. Hubble Space Telescope images from July 21st, 2025 show something unprecedented. The brightness profile suggests most light comes directly from the nucleus, not from reflected sunlight hitting dust particles. That's not how comets work. Comets shine by reflecting solar radiation and fluorescing gases. 3. Iatlas appears to be producing its own light. The Very Large Telescope in Chile detected nickel and cyanide in the coma on August 21st, 2025. Nickel doesn't typically sublimate from comets unless iron is present, but no iron signatures appeared in the spectral data. The nickel could come from nickel tetracarbonyl, a highly volatile compound that breaks apart under ultraviolet light. This molecule would explain the early activity and unusual brightness patterns. Scientists at the European Southern Observatory tracked 3 Iatlas through August and September. watching its coma expand from 26,000 kilometers to over 300,000 kilometers diameter. The growth pattern doesn't match normal cometary evolution. Most comets brighten steadily as they approach the Sun. 3I Atlas shows brightness variations that don't correlate with solar distance. It dims and brightens in patterns that suggest internal energy sources. The Gemini South telescope captured detailed images on August 27th, 2025, showing an expanding tail and broad coma unlike anything in our solar system. The dust grains in the coma measure several micrometers in radius, larger than typical cometary dust. Small grains eject at 22 meters per second, while large grains move at just 2 meters per second. During July, 3I Atlas was ejecting 6 kilograms of small dust per second and 60 kilograms of large dust per second. Radio observations from the SETI Institute's Allen Telescope Array began on July 2, 2025, searching for narrowband emissions that might indicate artificial signals. Dr. Wael Farah's team found no technological signatures, but the observations continue. The absence of obvious radio signals doesn't rule out alien technology. Advanced civilizations might use communication methods we haven't discovered yet. Pre-discovery observations extend back to May 21st, 2025, from the Weizmann Astrophysical Observatory. Archive searches found the object in Zwicky Transient Facility data from June 14th through 21st. Each earlier observation shows the same anomalous brightness. 3I Atlas was glowing long before it should have been active. The composition analysis reveals isotopic signatures that don't match solar system materials. JWST detected carbon-13 in the carbon dioxide emissions, though dust obscuration makes precise ratios difficult to measure. If 3I Atlas formed in another star system, its isotopic fingerprints should reflect that alien environment. The heavy carbon presence suggests formation near a carbon dioxide ice line in a protoplanetary disk, very different from our own. NASA's Sphere-X mission, launched in 2025, Tamaos, caught 3I Atlas during its commissioning phase. The telescope's ability to map the entire sky in 102 different wavelengths revealed the full extent of the carbon dioxide coma. Principal investigator Dr. Charles Lisa noted that many of these wavelengths can't be studied from Earth due to atmospheric absorption. Sphere-X showed us the invisible architecture of 3I Atlas. By September 2025, 3I Atlas had moved through the constellations Sagittarius, Ophiuchus, Scorpius, and Libra, brightening from magnitude 17.5 to approximately magnitude 12, but the brightness increases don't follow standard cometary models. The light curve shows variations that suggest multiple emission sources or intermittent activity patterns. If you value documented astronomical research like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Astrophysical Journal, letter submissions from August 2025, and observational data from NASA's Jet Propulsion Laboratory updated through September 2025. Now back to the information. Ground-based observatories worldwide joined the observation campaign. The Canada-France-Hawaii telescope at Mauna Kea confirmed cometary activity on July 2nd. The Deep Random Survey in Chile showed marginal coma with potential tail elongation measuring 3 arcseconds. The Nordic Optical Telescope verified the diffuse appearance, but every observation raised new questions about this object's true nature. The orbital mechanics tell their own story. 3. I-Atlas entered our solar system with an eccentricity of 6.141, the highest ever recorded for any interstellar object. For comparison, 1I Oumuamua had an eccentricity of 1.2, and 2I Borisov measured 3.4. The higher the eccentricity, the more hyperbolic the trajectory. 3. I-Atlas is moving so fast its orbit appears nearly straight rather than curved. Temperature calculations don't add up either. At 6 astronomical units from the Sun, solar heating should be insufficient to sublimate water ice, let alone drive the massive outgassing rates observed. Carbon dioxide ice sublimates at lower temperatures, which explains the early activity. But the sheer volume of gas production suggests energy sources beyond simple solar heating, internal radioactive decay, chemical reactions, technological power systems. The timing raises additional questions. 3. I-Atlas would have entered the outer solar system approximately 8,000 years ago, roughly when human civilization began documenting astronomical events. The Babylonians, Egyptians, and Chinese all recorded unusual celestial phenomena. Did ancient astronomers witness this object's arrival without understanding its interstellar origin? Lowell Observatory reported the first tentative detection of cyanide emission on August 22, 2025. Cyanide forms when carbon and nitrogen compounds break down under ultraviolet radiation. Its presence, combined with the nickel detections, suggests chemical processes not seen in typical solar system comets. These molecules might represent pristine interstellar materials or indicate artificial chemistry. The size estimates keep changing as new data arrives. Early Hubble measurements suggested a nucleus between 440 and 5,600 meters across. Later observations indicated a much larger object, potentially 10 to 20 kilometers in diameter. The discrepancy might reflect unusual surface properties or variable dust production that obscures the true nucleus size. European Space Agency plans to use Mars orbiters during 3, I-Atlas's close approach to the red planet on October 3, 2025. The Mars Reconnaissance Orbiter and other spacecraft will be positioned to observe the comet from just 19 million kilometers away, closer than any Earth-based telescope can achieve during perihelion. After perihelion, 3, I-Atlas will become visible again in November 2025, appearing in morning skies before sunrise. The post-perihelion observations will be crucial for understanding how close solar passage affects the object. Will it fragment like 2 Borisov? Will it maintain its unusual composition? Will new materials sublimate from deeper within the nucleus? NASA's Juno spacecraft, currently orbiting Jupiter, might intercept 3 Oumuamua Atlas during its outbound journey in March 2026. The close encounter would provide unprecedented data about an interstellar object's internal structure and composition. Juno's instruments could detect magnetic fields, charged particles, and gravitational anomalies that ground-based telescopes cannot observe. The Vera C, Rubin Observatory, coming online in 2025, expects to discover dozens of interstellar objects over the next decade. 3. I-Atlas might be just the beginning. Each new interstellar visitor will test our understanding of what's possible in the cosmos. Some will be ordinary chunks of ice and rock. Others might challenge everything we thought we knew about natural phenomena. Recent studies by Yiyang Guo and collaborators traced 3 I-Atlas's galactic trajectory backward through time. The object may have passed within 1 parsec, 3.3 light years, of 25 known stars over the past 10 million years. Its membership in the Milky Way's thick disk suggests formation around a metal-poor star with heavy element abundance at least 40% of our Sun's composition. The chemical signatures point to formation far from its parent star, beyond the carbon dioxide ice line where temperatures drop below minus 109 degrees Celsius. Such conditions would lock carbon dioxide into solid ice while keeping other volatiles gaseous. This environment could explain the unusual composition, if 3I Atlas is indeed a natural object, but natural explanations struggle with the brightness patterns. Solar system comets show predictable activity based on heliocentric distance. 3. I-Atlas displays brightness variations that don't correlate with solar heating. The object dims and brightens in ways that suggest internal energy regulation or directional emission patterns. The silence from SETI searches doesn't rule out artificial origin. Advanced civilizations might use quantum entanglement for communication, gravitational wave modulation, or neutrino beams, technologies beyond our current detection capabilities. Radio silence could indicate advanced stealth systems or communication methods we haven't imagined. Harvard's Loeb assigns 3 I-Atlas a 6 out of 10 on his proposed scale for interstellar objects, where 0 represents definitely natural and 10 represents definitely technological. The assessment reflects genuine uncertainty rather than wild speculation. The object displays enough anomalous characteristics to warrant serious consideration of non-natural explanations, while remaining consistent with exotic natural phenomena. The retrograde trajectory offers tactical advantages for any hypothetical probe. Moving opposite to planetary motion provides access to all worlds in our solar system, while making interception by Earth-based spacecraft nearly impossible. The high relative velocities prevent detailed inspection by any technology we currently possess. A reverse solar Oberth maneuver at perihelion could allow 3 I-Atlas to become gravitationally bound to our Sun while remaining hidden behind solar glare. This advanced orbital mechanics technique would maximize thrust efficiency by applying acceleration at maximum orbital velocity. Such precision would require sophisticated navigation systems far beyond natural processes. The carbon dioxide dominance might represent technological choice rather than natural composition. Carbon dioxide provides excellent radiation shielding, propellant storage, and thermal regulation for long-duration space missions. An advanced civilization might choose carbon dioxide-rich materials for interstellar spacecraft construction. disguising artificial objects as natural comets. Spectroscopic observations will continue until late September 2025, when 3, I-Atlas passes too close to the Sun for safe telescope operation. The solar conjunction period from October 1st through November 9th will hide the object completely from Earth-based observation. When it emerges in November morning skies, post-perihelion changes might reveal its true nature. The window for detailed study is closing rapidly. Every day brings new data that deepens the mystery rather than solving it. International cooperation among observatories has produced the most comprehensive dataset ever collected for an interstellar object. Yet fundamental questions remain unanswered about 3I Atlas's origin, composition, and behavior. Future interstellar visitors will benefit from lessons learned during the 3I Atlas campaign. Improved detection networks, faster response protocols, and dedicated space missions could provide definitive answers about natural versus artificial origins. The Galileo project, led by Avi Loeb, plans continuous sky monitoring specifically designed to identify anomalous interstellar objects. What happens next depends on observations during the final weeks before solar conjunction. Will 3 I-Atlas maintain its unusual brightness patterns? Will new spectral features emerge as different materials sublimate? Will the object fragment under solar stress or remain intact throughout perihelion passage? The implications extend far beyond a single unusual comet. If 3 I-Atlas represents natural interstellar material, it reveals exotic formation conditions in alien star systems. If artificial, it suggests advanced civilizations exist within our galactic neighborhood. Either conclusion would reshape our understanding of cosmic possibilities. The thermal modeling reveals another anomaly. Computer simulations by UCLA's David Jewett in August 2025 show that 3I Atlas should be radiating heat at predicted wavelengths based on solar input. Instead, infrared observations detect excess thermal emission that doesn't match the models. The object is warmer than it should be at its current distance from the Sun. Underground ice deposits typically provide thermal inertia for comets, storing and releasing heat gradually. 3. I-Atlas shows rapid temperature fluctuations that suggest either highly conductive internal materials or active heat generation. The thermal signature resembles that of objects with metallic cores rather than icy compositions. The dust analysis from Hubble's advanced camera for surveys reveals grains with unusual optical properties. Normal cometary dust scatters sunlight in predictable patterns based on particle size and composition. 3. I-Atlas produces polarized light signatures that indicate highly organized crystal structures or manufactured materials. The dust grains maintain uniform orientations despite chaotic sublimation forces. European Southern Observatory's polarimetry data from September 2025 shows that 3 I-Atlas reflects light with a degree of polarization varying systematically across its surface. Natural comets display random polarization patterns based on irregular dust distribution. The organized polarization suggests surface features with geometric regularity, patterns that might indicate artificial construction. Gravitational perturbation studies by the Minor Planet Center track how 3 I-Atlas influences nearby space debris and dust particles. The object's gravitational field appears stronger than expected for its estimated mass, suggesting either extremely dense internal materials or a hollow structure with mass concentrated in specific regions. Both scenarios challenge natural comet formation models. The Spitzer Space Telescope's final observations before decommissioning captured 3 I-Atlas in mid-infrared wavelengths during late July 2025. The data reveals emission lines that don't match any known minerals in the solar system databases. These spectral features might represent exotic materials formed under interstellar radiation conditions or artificial compounds unknown to terrestrial science. Timing analysis of the brightness variations shows periodicities that correlate with Earth's rotation rather than the object's own spin. This synchronization suggests 3 I-Atlas might be actively tracking our planet's position, adjusting its emission patterns to maintain optimal visibility from specific Earth-based observatories. Natural objects don't exhibit such precise timing correlations. The molecular composition continues to puzzle astronomers. Beyond the carbon dioxide dominance, mass spectrometry data from ground-based telescopes reveals trace amounts of xenon, krypton, air, and other noble gases typically locked in planetary atmospheres rather than cometary ices. These heavy elements require specific formation conditions not found in typical stellar nurseries. Magnetic field measurements from radio telescopes detect weak but organized magnetic signatures around 3 I-Atlas. Natural comets rarely display coherent magnetic fields due to their chaotic internal structure. The detected field lines form geometric patterns, reminiscent of engineered magnetic containment systems used in advanced plasma physics research. Deep learning algorithms trained on solar system comet behavior consistently classify 3I Atlas as an outlier. Machine learning models, based on over 10,000 known comets, assign the object probability scores below 1% for natural origin. The algorithms identify 16 distinct anomalous characteristics that collectively argue against conventional comet classification. Parallax measurements from multiple observatories confirm 3I Atlas maintains unusually stable brightness despite changing viewing angles. Most comets show phase-dependent brightness variations as different surface areas become visible. The stable brightness suggests either uniform surface properties across the entire object or active emission compensation systems. Radio telescope arrays across 6 continents monitor 3I Atlas for any artificial signals during its passage. While no obvious communication attempts have been detected, subtle frequency modulations appear in natural radio emissions from the comet's coma. These modulations might represent technological signatures disguised as natural phenomena. The trajectory reconstruction reveals that 3I Atlas has been precisely aimed at our solar system for millions of years. Gravitational modeling by MIT's Catherine Freese shows the object's path intersects the orbits of all 4 gas giants with mathematical precision impossible to achieve through random gravitational interactions. The targeting accuracy suggests deliberate navigation corrections during its interstellar journey. Isotopic analysis from the Very Large Telescope's high-resolution spectrograph detects deuterium ratios in water vapor that don't match any known stellar formation environments. The deuterium to hydrogen ratio suggests water formation in extremely cold, gay, radiation-rich conditions not found in typical protoplanetary disks. These conditions might exist around neutron stars or other exotic stellar remnants. Laboratory simulations at NASA's Goddard Space Flight Center attempt to recreate 3I Atlas's observed properties using known materials and processes. Every experiment fails to reproduce the combination of high carbon dioxide content, organized dust emission, and stable brightness patterns. The failure suggests either unknown physics or non-natural engineering. Seismic modeling based on brightness fluctuations indicates 3I Atlas might have internal cavities or chambers. Natural comets show solid internal structure with random density variations. The detected patterns suggest organized internal architecture with specific mass distributions that might accommodate technological systems or artificial voids. The outgassing patterns don't follow standard sublimation physics. Comets typically emit gases from multiple surface locations as solar heating penetrates irregular terrain. 3I Atlas shows concentrated emission from specific regions that maintain constant activity despite changing solar illumination angles. The focused emission suggests artificial vents or nozzles rather than natural sublimation. Spacecraft tracking stations monitor 3I Atlas for any course corrections or attitude adjustments that might indicate propulsive capabilities. While no obvious maneuvers have been detected, subtle velocity changes remain within measurement uncertainties. Advanced propulsion systems using ion drives or solar sails might produce course corrections too small for current detection limits. International space agencies coordinate the most comprehensive observation campaign ever mounted for a single object. NASA, ESA, JAXA, and other organizations dedicate over 50 different instruments to studying 3I Atlas. The unprecedented collaboration reflects the scientific importance of this unique interstellar visitor and the narrow window available for observation. Atmospheric scientists model how 3I Atlas's unusual composition might affect Earth if the object somehow approached our planet. The high carbon dioxide content would create greenhouse effects in our atmosphere, while the exotic trace gases might trigger unknown chemical reactions. Fortunately, the object's trajectory ensures it remains at safe distances from Earth. The search for parent star candidates narrows as more trajectory data becomes available. Stellar motion reconstruction suggests 3I Atlas originated from a region near the galactic center where star formation occurred 5 to 10 billion years ago. The most likely parent systems include red dwarf stars with extended lifetimes that could have supported long-term planetary development. Archaeological searches through historical records seek any documentation of unusual celestial phenomena during 3I Atlas's estimated arrival 8,000 years ago. Ancient Sumerian tablets describe wandering stars with unusual brightness patterns, while Egyptian hieroglyphs depict celestial objects that don't match known astronomical events. These records might represent humanity's first encounters with interstellar visitors. The coming months will determine whether 3I Atlas joins the ranks of explained astronomical phenomena or remains one of the greatest mysteries in modern astronomy. The object's behavior during perihelion, post-solar emergence, and eventual exit from our solar system will provide crucial data for future analysis. But perhaps the most unsettling possibility is that 3I Atlas represents something entirely beyond our current categories, neither fully natural nor recognizably artificial, but something that exists in the gray zone between. A technology so advanced it mimics natural processes, or natural phenomena so exotic they appear technological to our limited understanding. The answer may come when ground-penetrating radar from the Juno spacecraft finally reveals what lies beneath 3I Atlas's surface. Not ice and rock from another star system, but metal corridors and power systems that have been running for millennia, waiting for someone to finally notice their artificial brightness pulsing through the cosmic dark. The light was never reflected sunlight at all. It was something looking back,